let's see where we're at. Okay, so on Monday, we talked about this idea of elementary operations, right? So elementary operations. And then the three types, let me say elementary row operations. So the first type of operation is to replace row I by -1 times row I. Right? So just multiply the row by -1. The second type of operation we saw was to replace row I by row J and vice versa. And then the third type of operation we saw was to replace row J by row J plus some integer multiple of row I. And we have similar operations for columns. Okay? So these were the three basic operations we saw that we could apply to integer matrices. And then the sort of main point is this idea that doing elementary operations is exactly the same thing as changing bases. Change of bases, both in the rows and columns. So just to remind you, because this will be useful in a moment, how it works. So say that, let me do it over here. So say that you have this matrix A, B, C, and D, which means that you have a basis x1, x2 in the domain, and perhaps y1 and y2 in the codomain. Correct? So if you do sort of the first type of operation, right, multiply, say, the first row by -1, that is equivalent to just multiplying this basis vector by -1 as well. That's the change of basis that you get. I want to talk about the third type of operation, which is the one that is perhaps a little bit more confusing. So here we go. So if we were to do the operation where, let's say, row 1, and we're going to use Python notation. So row 1 plus, let's say, lambda row 0. Then the matrix that you get looks like AB, and then C plus lambda A, and B plus lambda D, D plus lambda B. Correct? And then the question is, how did the basis change when you did that? So it turns out that when you do row operations, what changes is the basis in the codomain. So these guys stay the same, and this guy over here now looks like y1 minus lambda y2, and then this is y2. In other words, what it's doing is sort of is changing the basis of, I guess, the row that is operating, right? And it changes, and the changes by sort of the opposite of what you did to the other row. Okay. Let's see why this is the case. Okay. So if you have a matrix like this, what it is saying is that x1 is going to a y1 plus c y2, right? So that's what the matrix representation is telling you. So if this is true, then notice that this is also equal to A times y1 minus lambda 2 y2 plus c plus lambda a y2. Right, so if you multiply it out, you will see that this guy cancels with this guy, and you recover your a y1, c y2 that you had before, right? So it's sort of the algebraic trickery to keep everything consistent. Okay, so that's the first comment. Now let's see what happens if you do a column operation. So say that you change the column, so this column, you change it by adding, let's say, beta times the first column, right? So the matrix that you get now looks like A, and then here you have B plus beta A, here you have C, and this is D plus beta C. And now if row columns change the basis in the domain, then column operations change the basis in the domain, right? So here you're going to have y1 and y2 again. And it turns out that the basis they're going to have is x1 and then x1 plus beta x2. And let's see why that is the case. So again, x1 goes to a y1 plus c y2, and then x2 goes to b y1 plus d y2, right? So if you were to add, let's see, yeah, if you were to do, excuse me, yeah. So if you were to do, beta times this first, let's say, relation plus this relation, what you get is that x2 plus beta x1 now goes, because everything is linear, then it goes to b plus beta a y1 plus d plus beta c y2, right? Which is exactly the coefficients that you have in here and in here. So you're saying that this basis element is going to this, and that's why these guys appear here. Okay. So the thing to keep in mind, again, is that row operations change the basis in the codomain, and that when you do this, multiply a row and then add it to another row, the way it acts is sort of backwards. It acts on the row that sort of did the operation. In columns, you are changing the basis in the domain, and it acts sort of as one would say correctly, right? You're saying, I'm going to change this guy to this plus beta x1, and what changes is the actual guy that is right here. Okay? So columns are correct, rows are inverse. Okay? So we're going to use these very, very simple observation to start computing homology. And I guess the last thing we said was that one can use row and column operations. So this is called the Smith normal form. using operations, using row and column operations of types 1, 2, and 3. One can turn any matrix M, which is an integer matrix of size, say n by L, or L by n, into one of the form so very, very simple. So K1 through KB, and then everything else is 0. And then K1 divides K2, K3, K2. Okay. So now that through the very, very simple operations we described, one can change the basis so that the matrix now looks very, very, very simple. And the last thing we said is that one can use this type of thinking to compute homology. So what I want to do today is just run with this idea and actually show you a couple of examples of how to do that in practice. Okay? So let's get started. So I'm going to do, so how should we do this? Yeah, let's do it right. That's the way to do it, right? So let's start with the complex K, which is going to be the following. It's going to have 4 vertices. And it's going to have these triangular face. And as always, we label everything, which induces orientations, like so. I'm going to call this guy sigma. And then these guys here, it's important that we keep these correctly. So tau 0, tau 1, tau 2, tau 3, and tau 4. Okay. And I'm going to maintain 2 matrices. The first matrix I'm going to maintain is the matrix for delta 2, for the second boundary now. So remember that we have C2 going to C1, going to C0, and then going to 0. This is delta 2, this is delta 1. Okay? So as a matrix, this operates on 2 chains, right? So a basis for the 2 chains is going to be given by just sigma, because it's the only 2 simplex that we have. So the basis is going to look, so this guy in matrix form is going to look like sigma. And then in the column main, meaning here in C1, the basis is going to be given by the 1 simplices, the edges. So this is going to be tau 0, tau 1, tau 2, tau 3, and tau 4. What I'm going to do next is I'm going to compute the boundary of sigma. So if you look at sigma, its boundary is going to be tau 0 plus tau 1 minus tau 2. So tau 0 plus tau 1 minus tau 2. And then I'm going to leave the rest empty to signify that they are all 0. Okay? Now let's look at the other matrix, delta 1. So now this guy operates on from edges to vertices. So the vertices are going to be U0, U1, U2, and U3. And then the, I wish hopefully you'll remember this. You have it written, so. And then here we have tau 1, sorry, tau 0, tau 1, tau 2, tau 3 and 4. Excellent. And now let's compute the boundaries, right? So tau 0 is 1 minus 0. Tau 1 is 2 minus 1. Tau 2 is 2 minus 0. So 2 minus 0. Then tau 3 is 3 minus 0. And then tau 4 is 3 minus 2. So 3 minus 2. And then the understanding is that everything else is going to be 0. Okay, before we begin sort of doing operations in this matrix. So what I'm going to do next, I'm going to do row and column operations of type 1, 2, and 3 to both of these matrices. And I'm going to do it at the same time. But before I get to that, let's check our intuition of what the homology of this space should be. Okay? So if we compute H0 of K, what should we get? So remember that 0 is the number of path connected components, right? So it has only one connected component, so it should be just only one copy of Z. H1 is looking for one-dimensional holes in the space. So there's one here, so we should see Z. And the other one should be 0, because there are no other high-dimensional holes, correct? So let's start doing some reductions on these matrices. Okay. So I'm going to try to be very, 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 very careful so that the algebra doesn't betray us. So these are the operations I'm going to perform on delta 1. I'm going to just list them out. So the first thing I'm going to do is I'm going to turn this row positive. So I'm going to multiply by -1. So row 0 is going to be -1 times row 0. Okay? Right. Once I do that, oops. Okay. Once I do that, once I turn this guy into a 1, this guy into a 1, and this guy into a 1, I'm going to use column operations to zero out these two guys. Okay, so I'm going to do, I'm going to change the column 2 for column 2 plus -1 times column 0. Right? And then I'm going to do column 3. I'm going to replace it by column 3 plus -1 column 1. Column 0. Okay. And let's see what happens when I do that. Okay. So now the first row is going to be positive. So the first entry that I'm going to have here is going to be a 1. And then the basis element is going to be minus U0. That's what this operation is going to do to the basis element. And then we're going to have a 1 in here, which is just of U1. So since I only did one row operation, this is the only basis element that is going to change. The other ones are going to stay the same. So this is going to be U2 and U3. Now let's look at how the columns are changing. So now this is tau 0. Tau 1. Right, so that doesn't, nothing happens there. So minus 1, 1. And then when I remove these guys, then the basis that I get, what's that?
Nothing.
Okay. So you get here tau 2 minus tau 0, minus 1, 1. I'm going to write it out and see. Minus 1, 1. And then tau 4. Okay. So again, just keeping track of what operations I'm doing and how they change the basis elements. To make sure that, I mean, you can look at the matrix and check back with the complex to see that the formulas are still correct. But here's what I want to do. I want to look now at delta 2. So here's sigma, yeah?
So if you start by changing the first row, make them all positive.
Yep.
Then you're. Oh, never mind. Okay, I just did my signs back.
Okay.
All right. Yep.
Cool. Yeah, happens to the best of us. So this is sigma, and here's what I wanna point out. Once I did column operations in here, I changed the basis in tau, right? So that means that I'm changing how the basis in here looks like. So what I would like to do now is do row operations on delta 2 so that I match whatever basis I get here at the end, correct? So I would like to get the same guys that I have here, I would like to have them here. So I would like to have tau 0, tau 1, tau 2 minus tau 0, tau 3 minus tau 0, and tau 4. Okay? So, and the question is, what are the row operations that I have to do to make that happen? So it turns out that what you have to do is switch column for row, right? Because now we're doing row operations. We switch the roles of 2 and 0. So I'm going to have 0 here, 0 here, and 2 here. And if I did minus 1 here, I'm going to do 1 in here, the opposite. One can check that this is the actual operation that is going to give you the appropriate basis element in here. And the same for this guy at the end. So row plus 1 times row, and switch the roles of 0 and 3. Right? So from here to here, what you get is the following matrix. You get tau 1, 1, and minus 1 here. Okay? So we're just going to continue this process in which I do row and column operations to this matrix. I keep track of the operations to change the basis appropriately, both in rows and columns, and then I go back and mimic whatever operation I wanted to get the right answer here. Yes?
No, I got something wrong.
Just more at a basic level. So you only have to worry about the column operations you do to D1 for D2.
These two, correct.
Because you're actually changing the elements there. There's no row operations that are going to be transferred over. So, okay.
Yep.
Just making sure.
Yeah, that's right.
Yeah.
Okay?
The row operations affect the C0 basis, which doesn't exist at all in
I mean, it doesn't, I mean, C0 does exist,
Yeah.
right? But we just don't care about delta 0.
But I'm just saying, yeah, row operations on delta 1 affect the C0 basis.
Correct.
Which doesn't matter at all for delta 2.
Exactly right.
Yeah.
You're right. It does matter for for this computation, but we're not going to worry about it now. That's my point. Okay? Okay, so if you guys want to keep track of all the operations, we can, but let's not. Okay? I'm just going to leave it as a homework exercise and just tell you what happens at the end once you do all the right row and column operations to reduce the matrix as much as possible. So here's the answer. I didn't want to erase that. Okay. So let me say what happens at the very, very end. So in here, let me erase the bases. Boom. And let me say what happens at the very, very end of the algorithm. So you're going to have tau 0, tau 1, tau 2 minus tau 0 minus tau 1. Maybe we need a little bit more space. Let's start again. So here in the delta 1 arena, or delta, in the delta 2 arena, let's do that first. Delta 2. So you get sigma in here, you get tau 0, tau 1, tau 2 minus tau 0 minus tau 1, tau 3 minus tau 0 minus tau 1, and tau 4 minus tau 3 plus tau 0 plus tau 1. And the matrix that you get is just minus 1 here, right? And then the matrix that you get in here looks like U0, U1 minus U0, U2 minus U1, U2, and then U3 minus U2. And then in here, you get the same basis that you have there. Tau 0, tau 1. Yeah, I don't know if the music makes it more enjoyable, but this is the basis we get. Tau 3 minus tau 0 minus tau 1, and then tau 4 minus tau 3 minus tau 0 minus tau 1. And then the matrix looks like a 1 in here, a 1 in here, and then a 1 all the way in here. So, I mean, you really have to be careful with all these operations. It's very, very easy to get confused, especially because the way how the operations change the bases in the columns is flipped for the way it changes the rows in here. So you have to keep that straight. But if you're able to do that, you should get to something like this. So what is the upshot? What do we conclude from this computation? So remember that this is delta 1, right? Can anybody say one thing that we can conclude from these matrices? Yeah.
You can see, I feel like with the sigma one, you can see that's like the opposite of the border, right? You're going around, like you have your border of sigma basically defined.
Okay, cool. Cool.
Like you can see that.
Okay, so we have tau 0 minus tau 1, tau 2 minus tau 0 minus tau 1, right? So that is tau 2 minus tau 1 minus tau 0.
So we're computing everywhere where it's one, is it a boundary
Cycle.
cycle?
Right? We've just computed a one chain whose boundary is 0. So this is a cycle. this is another cycle. And what cycle is that? Is the cycle that does T4, and I guess minus T3, tau 0, and tau 1, right? So it works.
Would be
Isn't there redundancies in this?
Correct. Can you say why?
Not mathematically.
No, but like philosophically.
What? Oh, because they're technically different cycles, but they're over the same boundary?
Over the same hole.
Over the same
Yeah.
homology?
Over the same hole. Okay, let's take the difference.
Then the
Go ahead.
cycle doesn't go over the same hole, right? The tau 2 minus tau 0 minus tau 1, that never actually goes over a hole.
No, but these are two cycles. But I guess what I wanna
Like they're not homotopically equivalent cycles, right?
big words. But this shows the following. Remember that delta 2 and then delta 1. What happens when you evaluate delta 1 composed with delta 2?
0.
It's 0. So in particular, every boundary should also be a cycle. Right?
Okay.
So
should tau 0 be plus in the last one?
maybe. Yeah.
Yeah.
Right. So even having the answers, you can make mistakes. Yeah. It's plus.
Same, maybe not the same hole, but the same face?
No, not even that. Sort of this guy here
Okay.
is encoding the whole.
Yeah.
If to this guy you remove this boundary, it gives you this other hole,
Yeah.
which is the hole of the space. What else can we? Okay. I think we're ready actually to compute homology from these matrices. So, okay, so the first thing to notice is that the cycles, so Z1, KZ, is what? Is all the things that go to 0, okay? So it should be all the integer combinations of these plus that. How should we do this? Let me do it the following way. I'm going to call zeta 1. I'm gonna use zeta 1 for this guy, and allow me to take a minus, just because, okay? So that it goes in the right way. Right, so this should be tau 2, tau 0 plus tau 1 minus tau 2. Okay? So this is the boundary of sigma. Now, let's let zeta 2 be the other one, this guy. So it's going to be tau 4 minus tau 3 plus tau 0 plus tau 1, which can also be written as tau 2, let's see, tau 2 plus tau 4 minus tau 3. Okay. Okay, great. So zeta 1, which is all the cycles, is going to be sort of the kernel of this matrix, right? So it's all the combinations of this guy and this guy. This is zeta 1, or minus zeta 1, and this is zeta 2. So this right here should be something like n times zeta 1 plus m times zeta 2, and I'm allowed to take n and m in all the integers. Now, what are the boundaries? If you look here, the boundaries are all the things that look like the image of this guy. So it's all the generated by this guy here, which is sigma 1, zeta 1, right? Or minus zeta 1. So the boundaries are all the guys that look like k times zeta 1. And when we compute homology, let's say the first one, we're doing all the cycles mod all the boundaries. In other words, we are saying, give me all the guys in here. So the guys in here are similar if their difference is a boundary. So it essentially kills this contribution right here from zeta 1, which is the boundary piece. So this is really just the class of M zeta 2 and N and Z. And look who zeta 2 is. So zeta 2 is going around like that, which we've seen is the same thing as going around like here, because it differs from by a boundary. Okay. So we got the right answer. So hopefully this demystifies this computational homology a little bit. It really is just a matrix, a very careful matrix reduction, in which you have to keep track of row and column operations, and then at the end, since you did it correctly, the things that appear in here will also appear in here at the bottom, and you will be able to sort of cancel out whatever you have to cancel out. Correct? Any questions before we continue? Yep.
So just trying to then consist of when we would then, if we wanted to then use the same method to compute, the number of connected components, then we would use like D1 and D0. We use
Correct.
D1, D0 matrices. But what would they, and they would look similar where we would get, I'm just trying to think of like what would the actual components be that you would see.
Right, so this matrix is going to be the zero matrix, correct? So you really only need to worry about delta 1,
Okay.
correct? Which is the one that we computed here, right? So he's saying that, yeah, this is a good example here.
You look at the rows. Oh, okay.
It's right here,
Gotcha.
right? So he's saying that this guy is generated by these bases. This, and that. Now, this guy here is hit as a boundary. So it's someone that comes from here, so we remove it in the sort of denominator part here of the quotient. The same for this guy, is hit as a boundary. So we remove it. And this guy here is also hit as a boundary. The only guy that survives is U2, which is the vertex. And if you guys remember the computations we did on Monday, in the end, age 0 was generated by one of the vertices, right? And it's because of this. Yeah, that was a good question. Okay. Cool? So it's just matrix reduction. A very, very careful matrix reduction. Pair of matrix reductions. Okay. Let's do something fun.
We gonna code it from scratch?
What's that?
Are we gonna code it from scratch?
Nah. I mean, you could, but nah. Let me not stop you. Let me say that, right? So you can definitely code it if you want.
So, what happens if, okay, this is like Gaussian elimination. What happens if your pivot isn't 1? Do you have to swap to a different
In Gaussian elimination, we're allowed to divide by things. When you have integers, the thing that you can do is take greatest common divisors.
Okay.
And then there are some special there's a special order of operations that allow you to use the greatest common divisor of the pivot in the row. So yeah, so let me say another way. So say that you have here like, I don't know, 5,
Okay.
right? And here in the row you have, I don't know, 7.
Okay.
So 5, let's not say 7, let's say 5 and 8. So 5 does not divide 8, right? So what you do is you find the greatest common divisor of the two, which is 1, and you find the linear combination of 5 and 8 that gives you 1.
Okay.
Okay? And you use those coefficients to change the pivot, to improve the pivot.
Okay.
And you do that a bunch of times, and the result is that at some point you're going to have a pivot that divides every single element of this row.
Okay.
And then you can kill things
All right.
via multiplication. Okay? Okay, I want to show you at least one example of how these ideas appear in data science. Jesus Christ. This seems excessive. Okay.
Like one of us would have to hold it.
Yeah, I was gonna say, just.
Okay, so I want to do a data example to indicate how these ideas appear in data science. So here's the example. In machine learning, you have a type of neural network that is known as an autoencoder. What are autoencoders? So you have a neural network where you have a first layer that has as many neurons as features in your data, correct? So if your data lives in, let's say, 5-dimensional Euclidean space, they're going to have 5 input neurons in here. Okay, step 1. Step 2, you're going to have an output layer of the same number of neurons as you had in the input. So again, if the input is 6-dimensional, then the output is also going to be 6-dimensional. Then you're going to have a layer in the middle that is going to have less neurons than the input and the output. And then the goal of the network is to learn the identity map. What does that mean? You're trying to train the weights in here so that when you pass a vector through the network, that same vector comes out as unchanged as possible. Why would you do that, right? So if you have very few neurons here in the middle, then that gives you a way of compressing the data or doing dimensionality reduction, because we started with a bunch of features and then perhaps a very, very few number of features in here. Okay? So it turns out that if you train an autoencoder on image patches from natural scenes, it has been observed that if you ask, so say that you're training, I think this was like 10 by 10, like 10 by 10 image patches from natural scenes, right? So you throw those through the network, right? So you're gonna have 100 inputs here, 100 inputs here, and maybe 10 here in the middle. And you ask, for each neuron, what is the input image that most excites that neuron? Okay, you ask that question. So it turns out that these are the types of images that most excite the neurons in an autoencoder trained on natural images. Okay? So this gives us a data analysis opportunity. one can ask, if we were to try to understand the behavior of this neural network, or if we were to try to understand sort of what is the structure of the main features that the network is detecting, we could ask the data science question of, what is the structure of this data set? The data set of images that look like this. Okay? So, I did just that. So I generated a bunch of images that looked like the ones from before, these edge detectors. I did that synthetically. So these are going to be 7x7 grayscale images depicting a line. And the line can be in any orientation and in any position within the patch. You can even leave the patch, meaning that you're going to get the empty image or the black image. Okay? Since these are 7x7 images, we can do one more thing, which is intensity center them. What that means is that if you average the pixel intensity in each image, you get 0. Okay? And then the final thing we're going to do is we're going to treat each one of these images as a vector in 49-dimensional space. Correct? Just 7x7, I just put the columns together into a long vector. And the question is, let's just do data analysis on this data set and see what happens. So here's the first thing I did, right? So something very, very simple. So there is a technique called principal component analysis. How many of you know what principal component analysis is? Mostly everybody. So what the idea is, you have a data set and you're looking for the directions in which variance is maximized. In other words, if you were to project the data onto this direction, you would get a good chunk of the variance in the data. A projector coordinate. Okay? So I did PCA on the data, and I plotted the percentage of variance from the data that is recovered after projecting onto the first, second, fifth, first 5, first 10, and first 15 principal components. Okay? So for the practitioners, people that have used PCA before, if you were to see a plot like that, what does that tell you?
It's not PCA. It's not doing very well.
PCA is not doing very well, right? So, one hypothesis could be that the data set is just very high dimensional, right? That it occupies a lot of space. So it needs to go up to, 15 components to actually get a good chunk of the variance, something like 80%, okay? Another hypothesis could be that the data is just sort of highly non-linearly embedded, right? So it's very twisted. Let's think about the data set for a second. So the data set is images that look like that, correct? So each one of those images can be described in the following way. You can give me the angle of the line with the horizontal, and you can give me the displacement from the middle of the patch, right? So if you give me those two numbers, you should be able to recover the image, okay? So what does this tell you when you look at this plot? Yes?
We're going to need a third one for like
The width?
the width, yeah.
Constant.
Oh, it's constant.
Constant.
Yep.
Yeah. So this is telling you that the data set is essentially two-dimensional, right? It needs only 2 parameters to describe everything, but you need something like 15 dimensions to actually see it. So that says that it's very highly nonlinearly embedded, okay? So I did the next best thing. So there's this method called isomap. How many of you know isomap? Okay, if you were, great. So what isomap does is it sort of disentangles the data and then does a projection similar to PCA. Is that I think that's good enough. So even after you do that, you still have to go up to dimension 5 to get something close to 80% of the variance, right? So what do we have thus far? We have a 2-dimensional data set that even when you disentangle it, you still need 5 dimensions to see it. For the people that know math, that is telling you that the space has to be complicated. It cannot be something simple like, a sphere or a torus. It has to be complicated to need this many dimensions to actually see it. So utilizing tools from topology, perhaps we'll see it in this semester, perhaps we won't. We were able to determine that the right space for the data, in other words, the space that parameterizes the data set, is RP2, the real projective plane. Let me explain these carefully. So first, let's see what RP2 is. One model for RP2 is the following: start with a disk, and then identify points in the boundary that are diametrically opposed. In other words, we're going to paste this point to that point. We're going to paste this point to that point. You're going to do that for all pairs of antipodal points. If your brain is hurting because you're trying to visualize it, that's fine. That's why this needs 5 dimensions. It's because it's hard to visualize. Okay? Here is how the data actually fits inside RP2. Right? So this is part of the topology and math that we did to get it to work. So hopefully you can see that if you look at the radial direction, it is changing the orientation of the line. If you look at the angular direction, if you look at the radial direction, it is changing the displacement in the line. Right? So those are the 2 variables that we hypothesized parameterize the data. And then it suggests the following model. It suggests, angular direction parameterizing the angle of the line, and then radial direction parameterizing displacement. And in here, you can hopefully see that diametrically opposed points in the boundary are the same point. Okay? So that's why RP2 is the right model for the data. Okay? So what did we do? First of all, we started with a deep learning problem, which was we trained a deep net or a shallow net on a type of data set that is common. We found some features that were important, and then we did data science on the features. And what we found is that the space that describes the features is complicated. It's RP2. What I want to do now is I want to compute the homology of this space. Okay?
Wait, what do you mean by that?
Exactly what I said. We're going to take RP2 and we're going to compute its homology.
Could you please explain RP2 again?
Yes, of course. RP2 is the space that you get by taking a disk and then taking the points in the boundary and pasting them together if they are antipodal. Okay. Yep.
So in this process, you said first you extract the features of the data set.
Yeah.
You use the autoencoder.
Yeah.
My question is, if you run autoencoder different times, you will get different features, right?
Probably, but you would get a sampling of roughly the same space.
Still roughly the same space.
Right, so the actual images that you get may be different, but the space that they describe will be still this RP2 of edges.
And the images are from, looks like the MNIST data set or something?
No, these are natural scenes,
Natural
like pictures of outside.
So the parameterization only works if you have sort of this line kind of.
Behavior in your data.
Yeah.
Correct. But you're right. These can be seen in things like MNIST or things like, handwritten characters. Like I would expect to see these types of lines in those images.
Just not
Yep.
very sure. Still, the question I asked.
Mhm.
The autoencoder, the activation function is a non-linear function.
Correct.
So I think it's a non-convex
Optimization.
optimization. So how we can say it's still like we can.
That's a good question. So if you believe that, and don't take my word for it, but if you believe that when you train a neural network and you trained it well, it should discover the important features in the data, then these are important features in images, so it should arrive to one of those minima.
Okay.
Like even if because what you're asking is essentially what are the weights in the network in a way.
Yeah.
That's similar because you're asking what is the image that most excites this neuron. You're asking for something that is almost similar to the weights that connect to it.
And
Yeah.
what I know when we training the neural network, we use the method is we optimize by iterations.
Yeah.
And so it depends on the initial weights.
It completely does, but that's why I said that if you believe that by training a network correctly, you arrive to features that represent the data, then that is actually a way to tell if the training process went well, right? Like if you train the network and you arrive to features that have nothing to do with the image, then it should be very easy to trick the network.
Have you tested how stable it is based on those initial
No, these are all interesting questions. I just did one thing, which was I found the features, and then I didn't even find the features. Someone else found the features, and I analyzed the data set of such
It's
features.
related to the study by Dr. Carlson
Mhm.
on
Yeah, correct.
Klein model
Yeah.
natural images.
Yep. So, so here's what I want to do. I want to take RP2. Now, hopefully, I've convinced you that these types of spaces actually appear in data that people care about. So what we're going to do now is we're going to try to compute the homology of RP2. Okay. Okay. So here's RP2 again. A disk with a dipole points identified in the boundary. The first thing we have to do is to give a simplicial complex model of the space so that we can actually do computations. Okay. So step one, simplicial complex model. Boom. So we're going to take a hexagon, and the way we're going to think of it is, points that are diametrically opposed in the boundary are going to be the same. So this edge is the same as that edge, and then this edge is the same as that edge, going in the opposite way. And we put these vertices here in the middle. So that is right there an honest to God simplicial complex that recovers RP2. Okay, and then given the order on the vertices, we can orient the edges as we've always done. And the thing that I want you to notice is that the order, the arrows in the edges determine an orientation for the two simplices. Okay, so I'm going to denote by green this orientation, and by what is that? Orange. Looks like orange. By orange, the other orientation. Okay, and let's just do that for all the simplices. Okay. What I want you to notice is that if I take the chain, which is this simplex plus that simplex, right? What happens when I look at the boundary of this plus that? So I have this boundary like this, right? And here I have this boundary like this, right? So this edge is canceling out. And what is left is this like that and like that. Okay? So the upshot is that if the triangles that share an edge have the same orientation, then the edge cancels out when I take the sum of the boundaries. Okay? Is that cool? Okay. Now notice what happens between these two. These two have different orientations, so this edge is not going to cancel out when I do the sum. So what do? Minus. So minus this guy, meaning that the orientation now goes the other way. Now it's green, right? Now this edge also cancels out if I give this guy the minus sign. Okay? And I just do that for all the simplices. Right? I have the right orientations. Okay? So here's what we're going to do. Once we have this. I'm going to do two things. The first thing I'll do is I'm going to take a chain, one chain, specific one chain. So I'm going to take zeta, and I'm going to let it be u0, u1, plus u1, u2, minus u0, u2. Correct? So if you look at that chain, it's essentially this border right here. Okay? What is the boundary of that? is 0. How do I know? Because it starts and ends at U0. It's an actual cycle. Okay? I'm gonna take another chain. The chain I'm gonna call it I'm gonna call it phi, and it's gonna be the sum of all two simplices in K with the right sign. And what is the right sign? The right sign that I just put here. Okay? So here's a question for the audience. When I compute the boundary of these two chains, what do I get?
Should be 0, right?
No, it's not 0.
Isn't it?
It's actually 2 times this guy. Let's see why. I chose the signs, right? So that all the interior edges cancel out when I take the boundary, correct? And what is left? The outer edges. And what are the outer edges? Are this guy, which is the chain that we just said defined as zeta, and then these guys as well, which is zeta again.
What do you mean by right sign again?
This is the right sign, the sign that I just put here in the picture.
All right, yeah.
It's the sign so that all the interior edges cancel out
So it's
when I take the boundary.
It's all the green triangles minus all the orange.
Exactly right. All the sum of all the green triangles minus the sum of all the orange triangles. Okay? So you get twice this guy. So here's something that I'm not going to prove, but that one can check by doing the type of matrix reduction that I explained at the beginning of the class. One can show that if you compute zeta 1, all the cycles, so all the cycles are actually multiples of the zeta. Okay, one can do again the matrix reduction to make sure that what I'm saying is true. One can also check that the boundaries are also all generated by this guy, by this phi. So in fact, this looks like 2 times KL, KZ, where K is in Z. Okay? Right, because again, by looking at the matrix reduction, one can see that you only get multiples of this guy, which is just 2 times sigma, 2 times zeta, which is this. So when we compute cycles divided by boundaries, modulo the boundaries, it's as if we were doing z divided by what? By 2z. Because one can think of this guy as 1, and here I'm taking all evens, right? And I'm dividing z by 2z, which is sort of 0 and 1. Okay, so this is tricky. This is the first interesting homology that we've computed in the class. What have we shown? Perhaps here I should put a zeta, that's better. So what have we shown? We've shown that the first homology of RP2 of the projective plane is Z mod 2. Z mod 2. And what does that look like? What is the interpretation? So it's saying that you have a class, meaning the class of zeta, which is not 0, but when you go twice around it, it becomes 0. Sort of mind-boggling, at least the first time you think about it. And this is the reason why I used integers as the sort of coefficients and for the computations. Next week we're gonna replace this guy here for other objects, and we're gonna see that may change the answers we get in the end. Okay, bless you. Let me give you a couple more examples and we'll finish with that. So, homology is a very computable invariant. We just saw that it's just matrix reductions. It's very computable. And the second thing is that it gives you sort of weird answers for spaces that are interesting. But not only that, these interesting spaces can also appear in data. I guess the next example I have in mind is the Klein bottle, which is related to your question before. So the Klein bottle is of two Mobius strips. So the Klein bottle is something that looks like this. So you start with a square. It's similar in the construction to RP2, that you start with something simple and then you paste it together in weird ways. So you start with a square, and what you do is you paste together the top and the bottom. That gives you a cylinder. And then what you do is you paste together the left and the right-hand side, but with opposite orientations. Okay? And what that gives you is something that looks like this. Draw it horizontally, but vertically is this. There's a company that sells this in glass. It's pretty cool.
By company, you mean Clifford Stoll?
Oh, I'm not gonna get into the debate. So that's a Klein bottle. Let's call it K. So the Klein bottle is cool because when you look at, let's say that you look at this path right here, okay? The path joining those 2 points. We said that this point here is the same as this point here in the back, right? So in particular, this is actually a cycle, okay? It's in fact this cycle. And then when you look at this guy, there is another cycle, right? Because you're identifying this side with that side, okay? So that's like the cycle that goes around this way. Here's what happens to this cycle. When you go around it twice, you filled in the cycle. And I'm going to be very hand wavy here. All of this to say that if you compute the homology of the Klein bottle, you should get C cross Z2. In other words, you get one of these guys that essentially accounts for this cycle, and you get one of these guys that accounts for the other cycle that has a similar behavior than RP2. So perhaps it is good to just write here RP2. Okay. So I think this is a good point to stop. So next time, next week, we'll go a little bit deeper into these types of calculations. And in particular, when I replace Z by field coefficients, like the real numbers or the rationals or Z mod a prime. And then all the problems really are Gaussian elimination. So we'll stop there. Have a good week. See you on Monday.